we are going to be talking about calculus on parametric curves. And I asked you to think about what the derivative of a parametric curve could be, right? So in the case of a function from R to R, the derivative is quite clear, right? So I should be quite clear. We've talked an enormous amount about it. So for point A, then the derivative is the slope of this tangent line, right? So f prime of A is the limit as h goes to 0 of f of A plus h minus f of A over h, which is exactly the slope of this tangent line, and the geometric meaning is clear. And the local information about how the function behaves is given by the tangent line. So what you need to understand things locally is just this number, right? Cool. All right. So that's in the case of a function from R to R. But a parametric curve, as we now know, is a function from R to R2, right? So we have a function which goes t into x of t, y of t. So let's draw a picture. So maybe it does something like this, right? And suppose we want to understand it at some particular point like this. Okay. Then what's involved? Well, there is the slope of this line, right? But that's not the only thing in play, right? That's not the only thing in play. Because as we know, this curve is not uniquely defined by this parametric equation. We could have another curve that goes over this, we could have another parametric equation that goes over the same set of points, but goes over at a different speed, right? So the slope at this thing right here is not the only thing involved, yeah? So we can't just assume one number gives you everything we need to know locally about this, you know? So what will we do? We will do what you'd expect us to do. We would just say, okay, here we are at A, so this is time A. If we move forward to time A plus H, so this is x of A plus H, y of A plus H, would have this point right here. And then we're going to consider the difference, what happens when we go from here to here, right? And we're going to divide it by H. Yeah. So the derivative of parametric curve at A is given by what happens, we take the limit as h goes to 0 of x of A plus H, y of A plus H, minus x of A, y of A over H, right? And we rewrite this so that the stuff is happening inside the actual coordinates of the vector. So that's the limit as h goes to 0, x of A plus H minus x of A over H, and then limit as h goes to 0 of y of A plus H minus y of A over H, right? And if these coordinate functions x of t and y of t are differentiable, then this thing is just equal to x prime of t, y prime of t, which is a vector, right? So if we have our parametric curve and we want to understand locally what's happening, then the information that we need to understand what locally is happening is some vector. And as you can see from this picture, as the vector will be going along the direction of the curve. Yeah? The direction this will be, as you look closer and closer, the direction of the vector is more and more like the direction of the curve. Yeah? Just because, as you look here, if we move forward a little bit and we take this thing getting smaller and smaller, it's definitely going to be like this, right? Yeah? But there's not just the direction involved in a vector, there's also the length, right? There's also the length. So The length of the vector will give us information about how fast this equation, x of t, y of t, this parametric equation, is moving through the set of points, right? If it's moving very fast, then this thing will be long. And if it's moving slower, then it'll be short. Yeah? Okay. How do you feel about that? Is that making some sort of sense? Yeah? So we considered two examples, right? We considered many examples, but we considered these initial two examples. If we had x of t equals cosine of t, and y of t equals sine of t, this was giving us the equation, parametric equation, which went around in a circle, like this. Yeah? So if we take the derivative at some point, what happens? X prime of t is equal to minus sine of t, and y prime of t is equal to cosine of t. And you notice that this vector is orthogonal to this vector, right? So this is the vector that gives us the position x of t, y of t. And this guy here is pointing orthogonally like this. Yeah? This is the direction of the derivative, right? It is pointing orthogonally like this. Yeah? Yeah? And if instead of this, we had this guy, x of t is equal to cosine of 2t, y of t is equal to sine of 2t. Again, it's going around the circle, but now it's going around twice the speed. So in the same amount of time, it'll do 2 wrap around the circles. Yeah? And if we take the derivative, then x prime of t is equal to minus 2 sine of t. And y prime of t is equal to 2 cosine of 2t. So again, this thing has its derivative pointing orthogonally, yeah, to it because it's on the circle, so it's tangent to the circle. But now notice that the length is bigger. It's actually twice as big, right? This vector here is twice the length of this vector here, right? Just as we were just saying. So the length of the vector encodes the speed. Yeah? So this is x prime of t, y prime of t in this case. Okay? So the key takeaway is that the derivative now is not a number, it's a vector. It's a 2 vector. And it has to be a 2 vector because it has to encode more information. Okay? Cool. All right, so that is the beginning of calculus. Given a parametric curve, even though the derivative of the parametric curve is a vector, right? Sometimes you want to talk about what the slope of the parametric curve is at a particular point. And when we say slope, we mean the dy over dx slope, okay? So we might want to know what the slope of this line is if we take the tangent line right here. Okay, we might want to know that. Or the slope when we take the tangent line right here. So the slope is not the derivative. Yeah, the slope is definitely not the derivative. But it is some definite quantity that we can see. There is a slope. When we stick on some line on a parametric curve, there is definitely some sort of slope there, right? Yeah, you can see there is a slope. Yeah. So we might want to actually find the tangent line to a parametric curve at some particular point. Yeah? And to do that, we're going to have to try and understand what the dy by dx slope is in terms of the derivative of the parametric curve. Okay? So we might want to find. So this is a key thing. Do not confuse the slope with the derivative. It is absolutely not the same thing. So I'm going to put this in quotation marks. Dy by dx slope at some point. say a of x, y of a. So x of a, y of a. Okay, let's see how we can do this. So let's say this is our particular point here. This is x of a, y of a, right here. Yeah? And we're going to take this thing here and we're going to blow it up onto a larger scale to try and understand how we can actually extract the slope. So this is your magnifying glass, or this is your microscope, zooming this picture up into a much bigger scale so we can see what's happening. So, what do we see? We see the curve is doing something like this. Yeah? We have some point here, which is x of a, y of a, right? And we have a straight line going through like this. We want to find the slope of this straight line. Yeah? So what could we do? Well, if we move forward in time, t doesn't have to be time, but it's convenient to call it time. So if we move forward in time to some point over here, then what point will this be? This will be x of a plus h, y of a plus h, right? Yeah, that's where this thing will be. Yeah? And then what we know about this point we move forward to? Well, since x and y are differentiable, we know that x of a plus h minus x of a is like h times x prime of a, and then some small error. So I'm going to put this as approximately. And we also know that y of a plus h minus y of a is h times y prime of h for some small error. Yeah? That's exactly what differentiability says, right? So the small error that we have here is much smaller than h, right? We've done this a number of times. Hopefully you're happy with this. This is the meaning, this is the point of differentiability, right? So if we look at this picture right here, to find the dy by dx slope, right, we're going to have to see how far up we go divided by how far along. Yeah? So the dy by dx slope is going to be something that, well, it's going to be exactly this thing, which is x of a plus h minus x, oops, let's put the y here, y of a plus h minus y of a over x of a plus h minus x of a. That's exactly this length here, right? Because this thing right here is x of a plus h minus x of a. And this quantity here, this side right here, is exactly y of a plus h minus y of a, right? So that expression right here is exactly how far up or down we go divided by how far along. Yeah? Give me the thumbs up if you're with me. Thumbs down if anything's unclear. Okay, cool. And then we use the fact that these things are basically like this with very small error. So this is approximately equal to h of y prime of a over h of y of a, which is just the other way around. This is y of a times x like this, which is just y prime of a over x prime of a. And that gives us the slope. So we can just calculate y prime of a and x prime of a, and we have the dy by dx slope. Yeah? And it's just from this picture. Nothing mysterious, nothing weird. Yeah? Cool. All right, so the dy by dx slope is slope at x of a, y of a is given by this thing. And the error that we might have here, because this quantity x of a plus h minus x of a isn't exactly equal to this error goes down to 0 as h goes down to 0, which is what we do with this picture as we get the exact slope at this point. Okay, so in the limit as h goes to 0, this is exactly the thing. Okay, So with this, we can find the points on the curve that have a particular slope, and that's something we're about to do in the next example. Yeah? Cool. All right, so harder is to think about the parts of this parametric curve that are concave up or concave down. Yeah? And that also comes down to a picture, but this case is one that's too involved for me to actually give it to you. So here is a trick that works. So but don't get too interested in this trick because it works most of the time, but it isn't the real reason. If you look at this expression here, what is this? This is dy by dt of a over dx by dt of a. Yeah? And if you do this completely nonsensical thing of cancelling the dt's on the top and bottom, then you get dy by dx, yeah, which is the dy by dx slope. Okay, and you might have seen explanations like this if you saw something like this in previous courses. This is nothing except a way to remember this formula. This is nothing except a way to remember the formula. So I say this just because you might look in the book or some book and see stuff like this, but do not take this as the real reason. The real reason, of course, is the picture, and the picture is straightforward. But you can do this kind of cheating trick that gives you the same kind of formula. And there's actually a reason why that works, which is not something I can go into, but again comes down to pictures. But the reason I say that is that if we want to find the second derivative, then what is that? So the second derivative, which tells us concave up or concave down, is what we do when we calculate d by dx of dy by dx, right? Yeah. But we have that dy by dx is given by this thing. So that would be like y prime of a over x prime of a, like this. Yeah? And then this thing will actually be what happens when you take the derivative d by dt of this thing, which you can do because these are all functions of t. So d by dt suddenly means something. So all of this stuff doesn't mean anything. This is all just kind of nonsense. But this thing actually means something over dx by dt. Because if you believe this, or if you accept this totally false thing of pretending the dt's are numbers and cancelling them, then you can cancel the dt's and you get the expression that you want. Yeah? And again, it turns out that this works. So this thing, where we take y prime over x prime and then we differentiate with respect to t, and then we divide that by the derivative of x with respect to t, that thing is something we can calculate because everything depends on t. That's a meaningful quantity. And it turns out this quantity is indeed giving us the second derivative. Okay? And I can't give you a fuller explanation. It's not hard. It is very much like this stuff. It's just pictures, but it's beyond the scope, and I just don't have the time to do it. So this is an unfortunate thing I hate doing, of just saying, okay, just trust me, believe me that this is true, believe this weird-looking formula. But later, you will, if you study maths to a high level, as I hope you do, you'll see why that this is true, and it's not anything really different than pictures like this. Okay, all right, but with these formulae, then we can actually calculate some things about specific parametric curves and graphs, and that's what we're about to do. Example 1. We have a parametric curve given by this thing. And we have various things to show. Show C, which is the curve, has two tangents. So let me write curve C given by this thing. Show that C has two tangents at the point 3, 0, and find their equations. B, find the point with horizontal or vertical tangent. Determine where the function is concave up or concave down, or the curve is concave up or concave down. Concave up is C up, and concave down is C down. And finally sketch it. All right. So let's get to work on this. Solution. All right, first part. Show that C has two tangents at this point 3, 0. Okay, so if we have x of t, y of t is equal to 3, 0, then when can that happen? Well, this implies that x, which is equal to t squared, is equal to 3, and y, which is equal to this thing, t to the 3 minus t, is equal to 0. So this happens when t is equal to plus or minus root 3, right? So we need t to be plus or minus root 3 for the first thing to be satisfied. And then if t is either plus or minus root 3, then that too is also satisfied. Yeah? Because it's root 3 to the power 3, which is 3 root 3 minus 3 root 3 when t is root 3. And when we have t is minus root 3, then this is minus root 3 times 3 plus 3 times root 3. So again, it's 0. So these equations are satisfied at these two different times. Yeah? So I'm going fast, but try and stay with me and pull me back at any point. Interrupt if things are not clear. Cool. So it seems from that it's plausible that there are two different tangents because our curve is passing through the same point two times, yeah? Or two different times, but let's see. So we know that so I'm always going to put quotation marks because, strictly speaking, this makes no sense. dy is not a function of dx. dy is definitely not a function of dx, so we can't just calculate dy dx. But this is the how far up or down divided by how far along slope, so that's why I write this dy dx. So we know the dy dx slope is given by y prime over x prime, which we can just calculate, right? So y prime is equal to 3 times t squared minus 3. And x prime is given by 2 times t. Yeah? So what is that going to be? That's going to be 3 of t squared minus 1 over 2 times t. Yeah? And then let's see what happens when we have the two different times. So when t is equal to root 3, then dy by dx, we put root 3 into this, is equal to 3 times 3 minus 1 over 2 times root 3. So that is 3 times 2 divided by 2, so it's going to be just root 3. Yeah? And then when t equals minus root 3, we put this into this formula, and what we're going to have, then we have that dy by dx is going to be equal to 3. Again, we have 3 minus 1. And now we're going to have 2 times minus root 3. So now again, we're going to have root 3 times 2 divided by 2. So start again, we're going to have 3 times 2 divided by 2. So it's just 3 divided by minus root 3. So it's just minus root 3 like this. Yeah? So these are indeed different slopes at different times. Yeah? Cool. All right, we can start to block in some little bits of information. So when time equals 0, this thing is going through 0, right? And we know that we are passing through the point 3, 0, which is right here at 2 different times, at the time root 3 and minus root 3. And when we're doing this, we have different slopes. So when we're going like this at time root 3, we're going up with this slope, something like this. And when we are doing this at time minus root 3, we are going down with slope something like this. Yeah? So that's some initial information that we know. Cool. All right. Second part. Find the points where we have horizontal or vertical tangents. Okay, solution. So we have a horizontal tangent when the dy by dx slope is equal to 0. Yeah? So H tangent when dy by dx is equal to 0. And when's that going to happen? Well, this is a general expression for the slope right here. Yeah? Yeah? And that is dy by dx. So we require this thing to be equal to 0. Yeah? We require this thing to be equal to 0. Yeah? So that's equivalent to having this thing equal to 0, which is 3 of t squared minus 1 over 2t is equal to 0. Yeah? And that's only going to happen when t squared is equal to 1. Yeah? So happens when t squared is equal to 1, i.e. t is equal to plus or minus 1. Okay, so that also somewhat starts to fit because this thing here is either time root 3 or time minus root 3, right? Okay, and what we found out is, I mean, this here is time 0 here. And what we found out is that when we have time either 1 or plus 1, we have a horizontal tangent. So something like this is happening here. Yeah? Cool. And then what about vertical tangent? That happens when we have the dy by dx slope is equal to infinity. Yeah? Yeah? And when does that happen? That has to happen when this thing blows up to infinity, which is going to happen as t approaches 0. Yeah? So when dy by dx goes to infinity, and this is when t goes to 0 because of this expression right here, right? Yeah? So at t equals 0, we're going to have a vertical slope like this. So it starts to sort of make sense. We expect something to go like this, just connecting up the dots like this. Yeah? Like on curve sketching of the function from x to y, it's like a kind of detective novel that you have these clues and they start to fit together in a consistent way. And if they don't, then probably you've got a calculation error somewhere. Yeah? All right, cool. Everybody happy with this so far? I realize that this is a new topic and it's not an easy topic, and that I'm going pretty fast. But are you hanging in? Is there anything which, before I erase, you want me to talk more about? Okay, cool. Let us keep going with this. So we found the horizontal vertical tangents. We need to find where this thing is concave up and concave down. All right, so this is our guy. Y of t is equal to t squared. Sorry, x of t equals this. Y of t is equal to t to the 3 minus 3t like this. Yeah? And now we want to find C, where is it concave up and concave down? All right, so we've learned that this thing, the second derivative, which I'm going to put in quotation marks, d squared y by dx squared, quotation marks, this is what we get when we take the ordinary slope, which is given by y prime over x prime over x prime of t, right? That's the dy by dx slope. And then we differentiate this with respect to t, and then we divide this by x prime of t, because it's this cancellation of the dt's on the bottom thing, okay? This is the formula that we have. So we've already calculated that dy by dx was what happened when we have 3 of t squared minus 3 like this over 2t, right? So this is an expression in t that we actually have the right to differentiate with respect to t. This makes sense. It's a consistent thing to do, right? So we can differentiate this thing with respect to t. So what is this thing? Well, we can clean this up a little bit. Let's factor out a 3 over 2. And then what does this thing become? This thing becomes just t, and then this thing becomes minus 1 over t like this, right? And then what is this? This is 3 over 2, and then this thing becomes 1, and then this thing becomes plus 1 over t squared, like this. Yeah? So that part is this part over here. That part is this part. Yeah? Cool. And then the second part is just the derivative of this thing with respect to t, and x prime of t, I mean, you just see what it is, it's just 2t. So the second derivative, like this, is equal to what happens when we take this thing and divide by this thing. Over 2, 1 plus 1 over t squared over 2t. So what's that? That's 3 over 4, 1 plus 1 over t squared over t. Okay? And then what's the sign of this? So this thing is going to be positive if t is bigger than 0, and it's going to be negative if t is less than 0, if t is less than 0, right? So what did we learn before? We learned that we have this guy like this, it does this, right? And this is the point 3, 0, and then does like this, yeah? And this is where we were at time I think it was root 3, right? Yeah. And this is where we were, I think, at time 1, right? So indeed, if we take time going forward, we're going like this. We're going down and up like this, yeah? And that thing looks like it's concave up, right? So on this part, it isn't concave up. So let me highlight this. This part here is curve for t bigger than 0 and is c up, which we can see. Right? It makes sense. It's consistent. And the other part is when we go down like this. Yeah. And that is curve for t less than 0, and this is concave down. Okay, we're out of, so anyone who needs to leave, we actually skipped part of the last example because we didn't find the equation of the tangent line at the point 3, 0. We just found the slopes, but hopefully we're good with finding the equation of the tangent line. But just for completeness, let me just say it. So we had this curve like this. We had 3, 0. We found that the slopes here was given by √3 and minus √3, right? So this slope here, as we're going forward in time, is √3. So the tangent line, so t line, would be t of x, and then it's the slope, which is √3, and then x minus the x coordinate, so x minus 3 plus where we are, which is just 0. So this is the tangent line at this particular slope here, at this particular point of the parametric curve here. So it's just √3 x minus √3 times 3, assuming I remember right that the slope was √3. Yeah. Okay, so that is for sketching and doing parametric curves. But there's other stuff we have to learn. So there's a couple of other notions. One of them is to find the area underneath a part of the parametric curve, and the other one is to actually find the length of the parametric curve. So let's talk about areas. So area on the parametric curve. So if we have some parametric curve like this, okay, and we want to know the area underneath it. So the way I've drawn this parametric curve, it does have a definite area underneath its graph. So for example, if we have a parametric curve which does something like this, we want to know the area underneath the curve from x of a, y of a to x of b, y of b, as I've shown here, then it makes no sense because we don't know what it can be possibly defined as, right? But if you have a setup like this, where for some part of the parametric curve, you have that there's just a direct straight line down to the x-axis where the curve doesn't over that particular time interval doesn't do anything else, right? Then we can ask, what is the area underneath the curve? This is a meaningful question to ask. Well, it's not meaningful here because we just don't know what we want to define the area to be. Yeah? And it might be tempting to go, okay, well, I'm just going to integrate from a to b this y coordinate, right? But that would make no sense because y is not a function of x, it's a function of t, which we're thinking of as time, right? So just integrating from a to b y of t doesn't necessarily give you anything like what this quantity is. This is just not meaningful. So it might look like it's the right kind of thing because it looks like the kind of formulas you've seen before, but it's just completely false, right? It's just completely false. So the way to actually find the area underneath this parametric curve is to do the following. So the area on the curve from x of a, y of a to x of b, y of b is given by integral from a to b, and we're going to integrate y of t like this, yeah? But we are now going to multiply it by x prime of t dt. And why so? Well, if you do this terrible trick of pretending that you can cancel dt's, then formally you can think, okay, I can just do this. So formally means just following some rule without thinking about it. And then that looks like the integral of y with respect to dx, right? And again, this makes no sense as I've done it, but it does give you the right answer. And it gives you the right answer because what's actually going on here? This x of t is how fast we're going in the x direction, right? Yeah. So if we were going very fast in the x direction as we integrate from a to b, then this thing would be quite a short time interval. Yeah. To get from here to here, if we're traveling fast in the x direction, then the time interval might be a lot shorter than the length of this thing right here. Yeah. And then this thing would compensate for it. So we might be integrating from, say, 1 to 1.2 in terms of time, and whereas this thing has got length 50. Yeah? But that means that the x coordinate's moving fast, and then this thing would be a very big quantity, which would compensate for the fact that we're integrating over quite a small range of numbers. Conversely, we could be going incredibly slowly with respect to the x coordinate, and therefore the time it takes to go from here to here could be 10 million, right? But if we're going incredibly slowly, then this thing would be very small. So we compensate for the fact we're integrating over a huge range of numbers with a very small number here. So in other words, this thing is rescaling things in the appropriate way so that we can think about this thing as being the area underneath the x-axis. Okay, and that's somewhat fast. But if you pause and think about it and just think about different scenarios, you will see that this is a reasonable thing to do if you want to integrate the area underneath the graph. Yeah? So with this, now it's just a formula, we can just do it. We can just explicitly do these calculations. This is another thing I sort of have to tell you to believe me on, which is a little bit frustrating because the reason is rather simple and geometrical, but I can't explain it here. All right, so find the area under the cycloid given by x of theta is equal to r times theta minus sine of theta, and y of theta is given by r of 1 minus cosine of theta. Okay, this thing forms a so-called cycloid under one arc. So if you're given a question like this, they will draw you a picture to show you that indeed you can integrate the area underneath because there is some clear notion of area. And the cycloid is something that does this. And the kind of methods which we did in the previous example allow you to sketch this thing, but this part will be given to you. So when we're at time 0, we are here. And when we're at time 2 pi, we are here. So this is x of 2 pi, y of 2 pi. And you can sort of quickly verify that. If you stick in 0, then clearly we have 0, right? Time 0, we're at 0. And when we're at time 2 pi, then the x-coordinate will be something. This distance is actually r times 2 pi. Yeah. So we're here, but the y-coordinate will definitely still be 0. Yeah. So one arc of the cycloid is just one loop underneath this. Yeah. That's what it's asking. So with the formula, then this is a triviality because we just put in the expressions, right? So the interval of time is 0 to 2 pi. Yeah. So we integrate from 0 to 2 pi. And then we have our y of t, which is here, or theta. I'm going to call it t because it's easier to write. So r of 1 minus cosine of t. That's the y. And then the x prime, we just differentiate it. So we have r and then 1 minus cosine of t like this, dt. So what's this? This is squared, the integral from 0 to 2 pi of 1. So we're going to multiply this stuff together, minus 2 cosine of t plus cosine squared of t dt. We use this double angle formula, not double angle formula, but this cosine squared of t is 1 plus cosine of 2t over 2. And then we put this thing into this thing, and when we do the integral, and it's just a standard trig integral, we know how to do this. Yeah? So once you have the formula, then this is just identifying what range of time gives us this particular arc, and then putting it in. Yeah? Not massively difficult. Yeah? We still have yet one more thing to learn, and that is arc length. Okay. Arc length. Of parametric curve. Yeah. So we've learned about arc length of an ordinary curve, right? So, I mean, a function from x to y, if we have some interval a to b, right? And this is the graph. We learned that the arc length was the integral from a to b of the square root of 1 plus f prime of x squared dx. And it just followed from looking closely at a small scale, drawing this triangle, right? And then seeing that this thing here, the hypotenuse of this small little bit, was giving us this kind of an expression. Yeah? Hopefully this is a little bit familiar, right? So that is when we have a function from x to y. And if you're familiar with this, if you're comfortable with why this thing gives this, then the next formula I'm about to give will also make sense because the reasoning is exactly the same. So if we have parametric curve, so x of t, y of t, and we want the length from a is less than equal to b, what are we going to do? So this might be what our curve looks like, right? But the strategy is always the same, right? We're going to look at some little small part of it, okay? And then we're going to say, okay, how long is this little part? Yeah? And because if we look on a very small scale, this thing is very nicely understandable because it's differentiable. So it looks an awful lot just like its tangent line. Yeah? And from that knowledge, we can calculate the small little bit, and then we're going to calculate for lots of small little bits and then add them all together. This is what I call the yin and yang of calculus. The two main ideas in play. The first idea is differentiability. We look at things on a very small scale, see that they are very much understandable. They are understandable as something like a linear function. And then the second idea is this generalized form of addition, which we call integration, of adding up these infinitely many small things and then taking the limit. This yin and yang work in this perfect conjunction to allow us to express quantities like this, which is the area which is the arc length of this function from x to y, and also the arc length of some parametric curve. So this is how we do it. So take large n and cut the time interval a to b into n equal pieces. Right, so we let t0 be equal to a, we let delta of t be this b minus a over n. And then ti plus 1 is equal to ti plus delta of t, and therefore tn is just the last time interval. So this thing right here could be x of tk, y of tk, and then this guy right here is x of tk plus 1, y of tk plus 1. So let's zoom in to what's happening here. We zoom in, and what do we see? We have our curve like this. This is where we are. X of tk, y of tk. Like this. And this is x of tk plus 1, which is the same of x of tk plus this delta of t. And then y of tk plus delta of t, like this. Yeah? So what we'd like to do is understand this quantity by approximating it just by the straight line that connects it, which is a reasonable approximation because it looks kind of flat, right? But that means we're going to draw a triangle, and we're going to see what this length is, and then what this length is, and then we're going to use Pythagoras, just as before, right? So what this length is x of tk plus delta of t minus x of tk, and what this length is y of tk plus delta of t minus y of tk, right? And as we've learned, this is very much like y prime of tk times delta of t, just by differentiability. And this thing is very much like x prime of tk times delta of t. So this hypotenuse here is this thing squared plus this thing squared, square rooted. So it's the square root of, let's do the x first, x prime of tk delta of t squared plus y prime of tk delta of t squared, and then that's delta of t square root of x prime of t squared plus y prime of tk squared, like this. And my formulas are overlapping, okay? And that thing is giving us a very good answer as to what the length of this little piece is, right? Just this piece. But we have n of them, so we add them all up. So add up all the pieces. We have the sum from k is equal to 1 up to capital N of these expressions. So it's going to be delta of t, the square root of x prime of tk squared plus y prime of tk squared, right? And then this thing is a Riemann sum. This is a Riemann sum. It will pass to a limit, right? It will pass to the limit. What limit will this tend to? What is this going to as we let n goes to infinity? Yes, but what will be the explicit formula? Where do we start in? Where do we start in time? Where do we end in time? Where do we start? Where do we end? Okay. So what will the integral be? So just think about the most basic version of Riemann sums, right? Just when we are using Riemann sums to approximate the area underneath the graph by taking these rectangles, right? And then this delta of x is the base of the rectangle, and then the height is given by whatever these points are, these xk, right? So then we have the sum k equals 1 to n of f of xk delta of x, and then that thing tends to the integral from a to b, right? F of x. That's how we defined the integral, yeah? Okay, so look at this expression. Now the integral is with respect to t, yeah, from a to b. What will we actually put inside this integral? Yep, and that's it. And that's it. So all you've done to go from here to here was just say let f be this expression, right? If we just let f be this thing, right? Then this thing is this thing, yeah? That's how we went from here to here, yeah? Cool. And then this is an exact expression for the arc length, yeah? And the reasoning is exactly the same reasoning as this. We just drew a triangle and applied Pythagoras to understand these little pieces right here, yeah? Yeah? Whereas previously, when the x-coordinate, we're moving like this, just with time 1, right? And the y-coordinate is the f of x, we get this. In the more general situation, then the x-coordinate is not necessarily moving with time 1, so we have x prime, y prime, yeah? Instead of just 1 and f prime. So this thing should seem rather natural if you understand this picture, and rather natural when you know this formula too. And in particular, if you are happy with this procedure, then all of these formulae that you're going to encounter in multivariable calculus follow in exactly this thing, exactly this way. You look on a small scale, you use differentiability, then you add up all the pieces with this generalized addition called integration. And we have all these exact formulae that otherwise we couldn't possibly find. You know? That's the power of this stuff. Cool. So with this formula, it's rather easy to just calculate the arc length of any curve. So an example for yourself, just use this to calculate the arc length of a circle of radius r, right? You can find the parameterization, so you know that x of t equals cosine of t, y of t equals sine of t. That thing's going to be something that describes a circle of radius r as we go from t is 0 to 2 pi. Yeah? And then just put this into the formula and find the arc length, and you'll find it's 2 pi r, which is what you know it to be anyway. Yeah? But now you know why it's 2 pi r, because this formula gives it to you. So doing the calculation is rather easy. Yeah? The thing I really care about is that you have some idea why this is true, and therefore are confident in using it. All right. So that's finally it. Thank you very much for all of you still here, for your patience. This was a super long class. Have a great weekend, and I'll see you all on Monday. Bye-bye, people. Start me off with a simple one so I can build up. What do we have? Okay, well, give me whatever you... Go ahead. Of half of theta, so let me call it t. Yeah. And is there some specification of what range of t we're doing? For t between negative pi and pi. Okay, so what is this going to sketch? Well, let us put the graph of sine and cosine. So sine is like this, and then cosine is like this. Right? And we are going from this range, so t over 2 goes from the range pi over 2 to minus pi over 2. Yeah, and so sine is going to go from the range of 0 to 0, and cosine is going to go from the range of minus 1 to 1. Right? So if we try and plot this, then sine goes from 0 to 0, cosine goes from minus 1 to 1. As you can see, it's part of a circle, so it's going to do something like this. Yeah? That's what it looks like. Yeah? And the question is to turn this parametric curve into an xy equation, right? Into a Cartesian equation. Is that the question? Cartesian equation is just equation in x and y, right? So we see that it's part of the circle. I mean, we know from the sine and cosine stuff that if we square sine and square cosine, it's just equal to 1. So we have that x of t squared plus y of t squared is equal to 1, yeah? And this thing we can't write as the graph of a function, typically, yeah? But because we have this convenient setup as the way it is like this, we see it's only half of this circle. So we could actually write this as the graph from the x-axis. Yeah? We could write this as the graph from the x-axis. And if we did this, then we'd have that it is a function from the y-axis. This is the y-axis, so x as a function of y is equal to the square root of 1 minus y squared. So then when y is equal to minus 1 here, then x is equal to 0, which is what we see, right? When y is equal to 0, which is here, then x is equal to 1, which is what we see, right? And when y is equal to 1, then x of y is equal to 0. So this thing for y, which is between minus 1 and 1, is now describing exactly the same set of points, but now it's a Cartesian equation. It's the equation with the x and y. It's called Cartesian because Descartes was this French philosopher, mathematician, who invented the notion of putting things on a plane with coordinates x and y. Okay, do you want to maybe give me another one? If you have another one. Oh, firstly, are you... you make the choice, but make it harder this time. But firstly, are you happy with this, and is everyone else happy with this? Yeah? Okay, all right, give me another one. Huh. Okay. And what's the range of t? Okay, yeah, all right. So let's think about this. So we'd like to write this as a graph of a function from x to y, and this remains positive, right? And this guy actually changes sign. So what happens? So the x coordinate's always positive, but when t is negative, this thing is also negative, right? So as t goes to infinity, then this is kind of growing like this. And as t goes to negative infinity, the x-coordinate's always positive, but the y-coordinate's negative. So it's going to be something like this, right? And it goes through 0. So I don't know if this is the way it curves, but I'm just getting some image. So then this thing looks like it's going to be something I can write as a graph from the, again, as a graph as x as a function of y. So x as a function of y. Yeah? So what do I see from this? I see that y, we can also think of as 1 over 9 of t, yeah? And therefore, if we wanted to write x as a function of y, so this is actually a different x. So now let me write this as capital X. So so this can be a source of confusion because it's a different x. Let me write capital X, and let me write capital Y. What will this be? Well, I can just plug in this t into this thing, and then I'll have this thing will be capital Y to the 2 over 9. And that does make sense, right? That thing will indeed, for every single y, this will be positive because of this 2 on top, and this thing will cover this graph like this.